Hi, it's me. We're going to pick up where that video was leaving off. My live demo that I did, I just wasn't super happy with it. I didn't end on a note I wanted to end on, and I realized there were some very subtle errors in the notebook I inherited from last year, but I think they're important. So I'm just going to re-record it. It'll go a little long, but hey, that's what the glory of 1.25 speed is all about. What we're going to do now is basically step through and do a demo of everything we've been doing throughout today's lecture, but now in Python, just to let you see that everything really does work. So in this notebook, our goal is going to be to fit a regularized, ultimately, logistic regression model. That is, we want to find the beta, which minimizes the average loss or the empirical risk. Okay. Now in this case, our model, our y-hats, are going to be sigma x transpose beta. So for every observation, we'll form the dot product with our beta, apply the sigma to it to give us a probability, and then we'll use L, some kind of loss, to give us the difference between our prediction and the actual observation. Okay. So given this model, right, if we're using this model, we can substitute in here. And then as we know from our previous lectures, the loss function that we want to use is the cross entropy loss. Just double checking that I'm actually recording and not just talking to myself. Okay, so here, if we take this cross entropy loss and substitute it into this expression, that is ultimately what we're going to try to minimize, but I'm not going to do that substitution because it just looks messy. Okay, so our goal is to find the beta that minimizes the average cross entropy loss. Okay, so nothing new there, but that's what we're going to do. Now, in terms of code, we can implement the sigma, the cross entropy loss, L, and the empirical risk using this code shown. So there's not a lot that's very interesting here. The prediction that we make is x multiplied by beta. One difference here is that in the version I was showing before, we were thinking about each individual prediction. Here, I'm doing all the predictions at once using matrix multiplication. We've seen that in a previous lecture, so I won't say anything else about it. This is our cross entropy loss here. And the empirical risk function is given here. So it's the average of the cross entropy loss for every observation and every prediction. Okay, so nothing so crazy there. All right, so let's see how we can optimize a model that does something useful using ultimately gradient descent. Okay, so we're going to consider this cancer data set, and it's a data set commonly used to demonstrate machine learning. The goal is, given all of these features, so we don't really care what they mean, things that doctors decided are important, like texture, perimeter, fractal dimension. We want to try and predict, is a tumor malignant or not? Malignant is bad, not malignant is good. So we're going to try and predict the ones that are malignant from all of these other features. Then we're going to start simple by only looking at the bias and the mean radius. Okay. So if you want, you can do some EDA with this, but I'm going to skip forward because this is more of a technical demo, not a data science demo. And so I'm going to start by splitting into a training and test set using my usual scikit-learn. And I'm not really going to run most of these cells today because the output's already there. But you can run the notebook on your own if you want to try out other things. So once I've made my training and my test split, where my training set has 426 observations and my test set has 143, we can plot our data on a scatter plot. Okay. So what does this tell us? Well, I didn't label my axes here again because this isn't really a data science lifecycle lecture so much as a technical demo. But here we see that if your radius is small, then, well, you're not malignant. If your radius is big, you are almost certainly malignant. And in the middle, well, the radius is not enough to determine for sure, but it maybe gives us some information. So if we wanted to try and fit a model here, as you know from your homework and labs, we can actually just do guess and check. I can try and guess a couple of betas that will give me a curve here that will best give me my probabilities. So I'm going to pick a different one here first. If I run this with beta 0 equal to minus 20 and beta 1 equal to 1, maybe I'll rename these beta 1 and beta 2. Doesn't really matter. If I name these beta 1 and beta 2, here are my betas, I get this curve. So is this a good model? I mean, not totally terrible, but I think I could do a little better. If I maybe pick something like minus 14, that looks better. Okay. How did I know to pick these betas? Well, I happen to remember from an earlier assignment that if this here, corresponding to our x down here, is 1, then the intercept will tell us roughly where the transition point is. Okay. So we could try changing this to be some other level of sharpness, but I'm just going to give you a sense that you can play around with it, but you've done that on a lab or homework, so I'm not going to waste lecture time doing it. Okay. So one way to evaluate the quality of the beta I've created is a plot like this, but another is to actually compute the average cross-entropy loss. Okay. So to do that, we're going to have to create a design matrix that we can feed to our function that computes the cross-entropy loss. So what I'm going to do here is this function returns a design matrix that has just the bias and the mean radius, and you'll see why this is useful in a moment. If I look at the shape of this object, it's 426 rows by 2 columns. The first column is the bias, the other one is the radius. Okay. We should also create a vector of our training data, and if we look at this, it's just going to be a vector of 0s and 1s. Okay. Maybe to convince you that this is actually the case, let's look at it. Okay. 0s and 1s. So not malignant, not malignant, not malignant, malignant. Okay. Now using our average cross entropy loss function, we defined way at the top, that was the empirical risk function R, I can compute the average cross entropy loss for a given choice. So if I pick -20, I get an average cross entropy loss of 1.17. If I pick -14, my better guess, I get a better number. If I pick -14.5, let's say, I get an even better number. And so in theory, I could actually do brute force gradient descent in this way by just tweaking these numbers until the output here gets smaller. So maybe I do 0.9. Is that better? No. Okay, well maybe I do 1.01. Is that better? I don't remember. Let's see. And so forth. I mean, you could do a process like this. Okay, this one actually is even better. Okay, so you could in principle do that over and over, but we want to try and do gradient descent. Now, in keeping with my general philosophy that I actually like to have short videos as opposed to long ones, I'll pause there and we'll pick up in the next video with gradient descent.